Alrighty, so last week we just talked about the first chunk of chapter 10. We talked about the valence electron pair repulsion theory and how the repulsion of the electrons in lone pairs and bonds cause the shape of molecules. So when we draw a Lewis structure, for example, ammonia, it looks very planar, but we learned that that is actually an oversimplification because there's electrons in the bonds that repel one another, and there's electrons from the lone pair that cause an even extra repulsion to actually give us a tetrahedral shape, which is a bond angle of 109. Give us our invisible lone pair up here, something like that, just very, very generic. So what I'm trying to tell you with that is this is also still an oversimplification because here we're still just thinking that two electrons come together to form a bond. But we learned in chapter 7 and 8 that electrons behave as particles and as waves. Us looking at two electrons coming together to make a bond is a particle view. But we know that electrons actually exist in orbitals. We know that there's an electron in an s orbital, then we have our different p orbitals. So, how can these orbitals come together to form a bond? Since an electron exists in an orbital, they actually have to overlap or come together to make the bonds. And that's in the two other theories we're going to be talking about today, which is valence bond theory and molecular orbital theory. So something I want you to kind of switch gears towards right now as we move forward is that the Lewis and valence electron repulsion theory are actually oversimplifications because we're just thinking that two electrons are coming together to bond. Even though there's repulsion going on, it doesn't give us too much insight on actually the shape of a molecule, and we'll see why in just a second. So valence bond theory says that the electrons reside in quantum numbers, we already know, s, p, d, f atomic orbitals are where electrons are located. We have orbitals that are hybridized, which is a blend or combination of two more standardized atomic orbitals. So before I give you too many just words, let's look at an example here. So valence bond theory says that, well, the bonds that are happening are because of orbital overlap, right? Because we know the electrons are in orbitals, and a bond happens because of an overlap. If we look at hydrogen sulfide, right? You have hydrogen, which is a 1s with a 1 electron, and another hydrogen with a 1 electron spin up in the 1s orbital. Then you have your s atom. We're looking at just the outer electrons, 3s, 3p. 1, 2, 3, 4, 5, 6 for my 6 valence electrons for sulfur. You can see that you have the 1 unpaired electron here and the 1 unpaired electron here, which will nicely bond with the hydrogen atoms. Now, with valence bond theory, we're saying that the orbitals are overlapping. So essentially, my s orbital for my H has my spin-up electron, and then my p orbital for my s has the other electron. The orbital overlap is what causes that bond to form that we see. So then you have all filled p orbitals and all filled s orbitals to actually get a bond that's formed. So basically now we're thinking, okay, so it's not just two electrons coming together to form a line, right? That's an oversimplification. We know that the electrons exist in bonds, and the way bonds are actually, the electrons exist in orbitals, and the way bonds are formed is through this orbital overlap to pair the electrons and give us the shape that we see. Now this works only for these cases. Let's look at a different example where it's not as obvious. Methane, Ch4. Now, if we draw the Lewis structure for Ch4, what would that look like? Let me switch to a pen here. I have carbon with my 4 hydrogens, right? Then I bond 4 times for a tetrahedral shape. Now, why is that possible? Let's look at the electron configuration orbital diagram for carbon and for hydrogen. So carbon, I have 2s2, 2p2, and each hydrogen has a 1 electron in a 1s. Now, notice here how I only have 2 electrons that are unpaired. So that would actually only let 2 hydrogens come in here, which would give me CH2, not CH4. However, experimentally, methane is actually a really, really stable molecule, and it exists in a tetrahedral shape. So scientists came together and said, well, because this exists, how is this possible? So then they took another step with the valence bond theory and made something called hybridization. Scientists said that in order for carbon and hydrogen to bond together 4 times, the 2s and 2p orbitals of carbon have to hybridize to make new orbitals that would allow 4 hydrogens to come together. So it would look like this. I would have my carbon, my 2s, right? And 2p is a little slightly higher in energy. My electrons filled. Now this does not allow for proper orbital overlap to make my bonds. I would then hybridize this. And hybrid meaning a combination of these 2 orbitals to make new ones to give me 4 new orbitals. These are called sp3. Think of one s orbital, right? And then the 3p orbitals to give me sp3. I now have 1, 2, 3, 4. 4 unpaired electrons in each of these orbitals, which would allow my hydrogen to overlap with these orbitals and give me my methane. Looking at a better diagram of that right here. So here you can see how the s and the 3p orbitals would come together to form the sp3 orbitals. A lot of the times when we're asking for hybridization, we just say sp3, or we'll learn some different ones, but just know that there's 4 of them, right? So then there's one facing in the direction of the px, the py, the pz, and the s orbital to give you a tetrahedral geometry of the 109.5 degree angle and allows the appropriate overlap for all hydrogen atoms, or any other atoms in that case, to bond with this carbon. It would look something like this. The new half-filled orbitals can now bond with 4 hydrogen atoms. So again, this arrangement is not possible for CH4. Because this is already a pair, we could essentially only overlap this orbital and make 2 bonds. For that reason, for that tetrahedral geometry, the s and the p orbital had to hybridize. They hybridized, they combined and made new orbitals. These are called sp3, where those 4 valence electrons of the carbon now distributed to 4 new hybrid orbitals to appropriately bond in a tetrahedral geometry with hydrogen or any other things in that matter that I would want to bond together in a tetrahedral shape. Now this is not only for carbon, this could be for anything that wants a tetrahedral shape. This is what it would look like. So you have your carbon. Now note how you have these 4 new sp3 orbitals and then the s orbitals of each hydrogen. So this is your s orbital of hydrogen, and these are your sp3 orbitals of the carbon. You have 3 of them. The overlap causes that pair of electrons. This would be your bond. Now, ammonia would be another possibility. Let's draw a little diagram just like how we did for carbon. So take a moment, follow along with me to draw the orbital diagram for nitrogen. So I have nitrogen, right, which I know has 2s, which is paired, and then 2p is slightly higher in energy. And how many electrons would I have in 2p? 1, 2, 3. Awesome. Well, I know that NH3 looks like this. We already went over that slightly. And this is a tetrahedral geometry. So I have to indicate that and hybridize my orbitals. So I would hybridize my orbitals. And something I want you to notice is, notice how when I draw my diagram of the hybridizations, my hybridized orbital or energies are in between the 2 atomic orbitals. They're not going to be higher or lower. If they're hybridizing, they're in between the 2 that are being hybridized together. So I would generate sp3 for my tetrahedral geometry. I have 1, 2, 3, 4, 5 electrons, where that pair in the sp3 orbital represents my lone pair. Then you can see this sp3 has my lone pair of electrons. This sp3 is the overlap with the H, so is this, and so is this, to give us our overall tetrahedral trigonal pyramidal specifically shape. Now let's look at another one, sp2. So one s orbital, which hybridized with two p orbitals. This would give us a shape like this. Notice how we've seen shapes like this before. When there's 3 electron groups around, this would be very generic for a trigonal planar geometry. You have an s orbital with 2 of the p orbitals to give us the following shape. An example of that is H2CO. Now, before looking at this complicated picture, let's take a step back and just look at H2CO. Let's draw the Lewis structure for that together. C, H, H, O, and the O would have to be double bonded to make my C happy. What shape is this? 1, 2, 3 bonding groups, no lone pairs, trigonal planar. So then I know carbon is my central atom, so let's look at that again. 2s, 2p, whoops, ignore that one. So I have my 4, right? Now again, I only have 2 unpaired, but I have an oxygen and the oxygen is double bonded, so this is not possible, and my electrons have to hybridize my orbitals. So then let's see what that would look like. I would have sp2 because I need 3 attachments. So this would be my sp2. And then I have one more p orbital where my other electron is, and this is unhybridized. Note how my unhybridized p orbital is in exactly the same energy as my p orbitals. Now, each of these sp2 orbitals will connect with my atoms, and this unhybridized p orbital allows for the double bond. Let's see what that would look like. I have my carbon, and I have my sp2 orbitals around each carbon, right? And then, let's change the color here. I have my oxygen, and I have my p orbitals for my oxygens. And my hydrogens with my s orbital. Boom, boom, boom. Awesome. However, carbon still has one unhybridized p orbital, which would then cause there to be something called a pi bond to give us that double bond. Boom, that looks so funky. I have a way better picture on the other side of this. But before I move on, let's just recoup for a sec. All right, we know this is trigonal planar, right? I need 3 electron groups, not 4, 3. So when I have my 4 valence electrons, 2 are paired in my 2s and 2 are alone in my 2p, they hybridize to give me that 3 electron geometry, sp2. Now I have my 3 lonely electrons, unfilled orbitals, to arrange in my trigonal planar shape. However, carbon has 4 valence electrons. I can't forget about the other electron, but that one's not hybridized. So there's one p orbital that has an electron that's unhybridized. So when I first draw my carbon with my sp2 orbitals, it will overlap with my hs orbital and the other one and a p orbital of my oxygen. But I can't forget that I still have this p orbital here for carbon. That's the reason that I have a double bond, because it'll overlap with the other p orbital of oxygen to give me something called a pi bond, and it looks a little bit funky like this. Woo, lots of words. Way beautiful, more beautiful picture. Instead of now saying covalent bonds, because we're not necessarily talking about just 2 electrons forming a line, we're talking about the hybridization. We have pi and sigma bonds that we'll be talking about when we're discussing valence bond theory. So here you can see I have my carbon and my purple, right, my sp2. My H's with the s orbital in blue overlapping here. Then I have my overlap with my p orbital for oxygen. And then I form another orbital with the remaining unhybridized p orbital of the carbon and an orbital of the oxygen. When you have orbitals that are overlapping side by side, you form something called a pi bond, which is just represented by the pi symbol. When orbitals overlap end to end, you have something called a sigma bond, which is represented by a sigma sign. Now, when you're doing problems like this, you show the electron geometry like we did and how they hybridize. You would show a picture like this, and then you would specify what is what. So notice how the overlap here, it's a head-to-head overlap, is 1 sigma bond. This is a pi bond. This comes from a side-to-side overlap, and it looks like this. So here's a little bit better of a picture. Notice how py and pz orbitals are coming diagonally in and out of the plane. They can only overlap side by side. So when they hybridize to come together, they form this little looking thing for a pi bond. The px is along the axis, right? So the other lobe is completely apart from the other lobe of the other orbital. The only way these two can overlap is through this head-on collision. Therefore, that is a sigma bond. S orbital and another s orbital can also only overlap this one time head-to-head, and it can also only form a sigma. So you can have 2 pi bonds and a sigma bond for your p orbitals, and only a sigma bond for your s orbitals. Now going again one step back here, this is just like the picture that I drew, right? Just prettier. So I have my trigonal planar sp2 orbitals for my carbon, right? And then I have a p orbital for my oxygen. Well, my carbon still has that unhybridized p orbital up here that looks like this, and my oxygen has a p orbital. Well, they overlap side by side to give us this red orbital looking here. And each of my hydrogen orbitals overlap with the sp2 orbitals of my carbon. Then you get something way prettier here that shows you the actual overlap, putting the bonds and orbitals together, including the hybridization of the carbon. Now, the way that we would describe this, I would say, all right, this bond here, this overlap, is sigma. The carbon, parentheses, sp2, is bonded with the hydrogen s orbital. Oops, I went on my other page. Then, this funky thing, right, is a pi bond, which is from my carbon, sp2, bonded with my oxygen, p. And then you would go through each one of these and explain them. Now looking at another one. So here we're talking a little bit about isomerism and why valence bond theory is helpful in describing the restrictions with things moving around. So notice these two pictures. Notice how here you have C that's a single bonded, right? And here you have 2 carbons that are double bonded. So when you have a single bond, you allow for free rotation because there's no limitation with the orbital overlap, right? Do you see how there's no, what should I say? There's no restrictions. There's nothing getting in the way. That's what I was looking for these two to rotate. Here with this double bond or even a triple bond, these pi orbitals are completely in the way and restrict for any way of these structures to kind of move around or rotate. So it tells you that valence bond theory helps understand how some rotation is restricted and some rotation is not restricted in molecules. And notice when it comes to isomers, isomers are things and structures that have the exact same molecular formula, but just different arrangement of atoms. So I could have an isomer of this structure where I have my chlorines across from each other instead of right next to each other like this. Now, the difference between isomers and resonance is that isomers, the only things that are moving are the atoms, not the bonds. But in resonance structures, all the atoms are staying exactly the same, but the bonds are moving around. Here's another example of that free rotation where you can see that when you have the single bond with the carbons, you can have complete rotation around the molecule. sp hybridization. Now, exactly what it means, S and P. So one s orbital and one p orbital hybridize to form sp hybridization, where you would still have unhybridized orbitals. Note, you have S and you have 3 P's. If these hybridize to only sp, you are going to have unhybridized p orbitals left over, always. They're not just going to go anywhere. These usually help in forming things with multiple bonds. For example, HCCH. Before I show you this picture, let's go through it together. Take a moment to draw that Lewis structure for me. Now I know carbon can bond 4 and the other carbon can bond 4, so I'm going to have 2 central atoms. My hydrogens are going to have to go on the outside. Well, both want 4, so I'm only left with making a triple bond in the middle. This is a linear geometry. Well, let's look at that again. Carbon, right? 2s, 2p. So now it would make sense, oh, okay, well, I have my 2 electrons here, so that's for sure where my hydrogens will bond, and the carbon. However, what about that pair? So here these electrons hybridize to form sp, and then 2 unhybridized p orbitals, where these help form your triple bond. So then let's look at the structure. You would have carbon and carbon. You would have your sp orbital and your sp orbital, and then the sp orbital here and sp orbital here. Then you would make your bonds with your hydrogens and your hydrogen. Awesome. However, you still have 2 p orbitals left over for the carbon. You have your py, your pz for both carbons that are unhybridized. So what they will do is they will overlap side by side with the other unhybridized p orbitals to actually give us a prettier picture like this. So here we have our linear geometry. In order to make this linear geometry, we had to have some unhybridized and some hybridized orbitals. Here you can see the hybridization causing the sigma bond between sp of both of the carbons and hydrogen and carbon. Then the 2 unhybridized p orbitals cause 2 pi bonds for the p orbital of C and the other p orbital of C, giving us our linear geometry. 2 more, sp3d hybridization. So now we have an s orbital, 3 p orbitals, and a d orbital hybridization. So what happens here? Well, notice how you have your energy diagram, 3s, 3p, 3d going up in energy. sp3d. This becomes when you have 1, 2, 3, 4, 5 electron geometry shape. So we need to make room for those electrons. 3s, 3p, and d come together to form sp3d hybrid orbitals. 1, 2, 3, 4, 5. With 1, 2, 3, 4 unhybridized orbitals. The 4 unhybridized orbitals comes from the remaining 3d. Remember that you always have those orbitals there for every element when it allows with the quantum numbers, even if they're unfilled. This allows us for a trigonal bipyramidal geometry. Example of that would be arsenic pentafluoride. 1, 2, 3, 4, 5 valence electrons and bonds with fluorine. So if we look at arsenic, we had to hybridize the orbitals just like what we've done so far to make room for the 5 fluorines that are coming together to bond with the middle, where then you form a sigma bond with the sp3d of the arsenic and the p orbital of the fluorine. sp3d2 hybridization. Now this is for our last one, octahedral geometry. S, 3 p's, and 2 d's give us 6 electron geometry. 1, 2, 3, 4, 5, 6, with 3 unhybridized orbitals. A great example is sulfur hexafluoride, where there's 6 fluorides that had to bond together with the sulfur. This shows you another example of why when you're in the 3rd energy level, this is possible. Because look, you have the d orbitals. And the reason this shape actually exists is because these orbitals rearrange and hybridize to actually allow the proper electrons to spread out to each of these orbitals so that they can then bond with just one singular fluorine. Now, little summary here, these are all your main hybridizations. For linear, sp, for trigonal planar, sp2, for tetrahedral, sp3, trigonal bipyramidal, sp3d, and octahedral, sp3d2. The reason that these orbitals are hybridizing is because the shape was not possible due to the different pairings of the s and the p orbitals. Therefore, the s and the p orbitals of different energy levels, or d, when we get to the third energy level or below, have to hybridize to make proper orbitals and allow electrons to fill around these orbitals so that they can bond and overlap with the proper atoms that they want to bond with to give us the shape that we see.